Hello calculus students, welcome to the continuing series of videos on summation and on series. In this video I am going to just show you some properties of summation. First of all, we can talk about the cases of factoring out constants. So here we have a summation of I times k, where k is a constant. So if we were to expand this, this would be like saying 1k plus 2k plus 3k all the way up to nk. But we can then just factor out the k, and we would have 1 plus 2 plus ... plus n. So this is the equivalent of saying k times the summation from I equals 1 to n of I. Okay. So see what we did there? We have this summation of I times k, and when we work this out, expand it, factor it, and then compress it down again, what we end up with is essentially the ability to factor out a k. So if you have a constant that's part of the summation expression, you can just factor that out. Similarly here, we could do notice here I have this n and this n, but in this case n is treated as a constant within the summation. So if I were to work this out, we would get 1n plus 2n plus 3n all the way up to nn, or n squared. But then we can just factor out an n, and we end up with 1 plus 2 plus 3 plus all the way up to n. So then we can just say that this is really n times the summation, because everything in this parentheses here is a summation from I equals 1 of I to n. Okay. So we essentially are able to factor out this n as well. So this is what we mean by factoring out constants. When the constant is something given to us, or the constant is something that's part of the summation itself, the ending part of the summation, we could always factor it out. And one more nifty and useful property here is the ability to separate a summation into multiple summations. So if I were to add this up, I would get 1 plus k plus 2 plus k. So notice here k is a constant, plus 3 plus k plus n plus k. Now, these parentheses I added here so that we can see each term, but mathematically and arithmetically, we really don't need them. We can remove them. So we can just rewrite this as 1 plus 2 plus 3 plus ... plus n plus k plus k plus k plus k. So we're going to rip out all these k's and just regroup them, and we're going to have n k, or n terms here. So what we effectively have is this first summation, which is the summation from 1 I equals 1 to I equals n of I, plus the summation of I equals 1 to n of k. So whenever you have an addition within the summation, we can separate it into two individual summations. So this right here and our final summation is the equivalent of each other. And you can also see that this part right here, this summation of k's, that's just equal to nk. Alright, now we move on to the next part, where we are going to do a random review question. So this says for me to evaluate this limit as n approaches infinity. Oh, this should be an x. No, actually, I'll change these to n's instead. So let me do a better version of this. This is the limit as n approaches infinity This is the limit as n approaches infinity of 3n to the third plus 5n squared minus 2 over 3n minus 2n cubed plus 5. So remember, all we really need to do here is look at leading terms. This is kind of like finding horizontal asymptotes. The leading term on the top is 3n cubed. The leading term on the bottom is negative 2n cubed. So this limit was equal to the limit as n approaches infinity of the quotient of the two leading terms, and we end up with negative 3/2. Okay, so this is a throwback question to like algebra 2 or something like that. That reminds us of how to take the limit as n approaches infinity of some expression where you have a polynomial divided by another polynomial. Okay? So I'll end this video here. We talked about summation notation, some basic properties of summation, and a review question that seems like it's kind of randomly just injected into there. I'll start another one where we get to the real prize of the day.